Okay, now it's loud. Sorry for the technical problems. You can start now.
Okay, sounds good. Thanks.
Mm.
Right. So just real quick, how many of you guys are familiar with quantization? Models, I guess specifically. If I didn't know that literature. Okay, so I'll just explain it from the start. Okay, so uh, basically what this paper is looking at is the ideas in sort of interpretability, especially in automated circuit discovery and for attribution to comprising language models. So the motivation of this is essentially that we realize that language models have weights that are very different in terms of importance. It's like a very power law kind of difference in importance, where some neurons are like tens of thousands of times more important to preserve when you're compressing a language. So usually, what people do is to locate like perhaps 1% or even less neurons important, and then when you let's say compress the model to low bit, such as 2 bits or 3 bits, you preserve these important weights in 16 bits. So what is essentially full precision. So in terms of like just some quick background on quantization itself, the most way to think about it is obviously that we're essentially rounding numbers into integers, basically doing a map that weighs on precision. But the what's done a lot of times is actually this like fancier thing where according to a particular small calibration data set, you estimate what the impact of rounding a particular weight is. So you would round this particular weight, let's say, in the middle of a weight matrix, like a 2D weight matrix, right, of a layer. You round the weight, then you figure out how does this rounding affect the output of that particular layer. And you would make sort of adjustments to the values of the other weights to try to compensate for whatever damage this did by quantizing a particular neuron. Does that part make sense? Right. Let me know if there's any issues. But yeah, the problem with this is most of these methods use calibration data, right, to figure out like the actual effect of quantizing a particular weight, right? So that's thing important to remember. And the second thing is for methods that select neurons to keep in 16, they do it like pretty naively. They basically, okay, well, there's a big activation coming into that neuron, probably important, and then they would observe it. Right? They would use some like just basically the absolute value of the gradient or the square of the gradient to figure out what weights are more important than others. So what we figured out in this paper is basically you can have a much better way of figuring out which weights are important by taking advantage of some ideas from the basically mostly from automated circuit discovery, and then you can basically locate these like weight circuits almost, right, as opposed to activation circuits, which is what the techniques originally applied. You can localize basically weights are sets of weights that are extremely important for the general performance model, but also for specific tasks. So we realized that most of these calibration data people use are from pre-training data of a language. A lot of times language models are like applied for specific tasks, where it's like like you're trying to have a medical robotic system. Like it does not need to know about abstract algebra. So, obviously, there is some task specificity that is important, right? So if you just use more specific calibration data, then you also get an improvement on top of the improvement you already observe from getting better localization. Yeah. In some sense, like the improvement in accuracy we see from using calibration is also dependent on the fact that we have a better localization method, because basically like some weights are more important for tasks and other weights are less important. Okay. So here's the part that might be interesting. So basically what we're observing here is a method that is composed of two different ideas mainly. The first idea is mostly from automatic circuit discovery and some from and sort of divided by localization as well. So mainly knowledge localization, I think people do for model editing before it was kind of like it's proven it basically kind of did not localize very well. But the ideas that they were do have like significant merit because they're also like mathematically backed and we can show empirically that it works. So the first idea is this quantization aware localization. So it's like a very common thing to do obviously in automated circuit discovery. You have a corrupt model, you have a clean model. And the corrupt model is literally just a clean model, except you have some like corrupted input, right? And to efficiently determine like what parts of the model are more important, or more precisely, like what activations are important, right? What we do is, okay, like for a particular task, we have a clean input and a corrupt input that would make the model run a particular task. They would subtract the intermediate activations from both of these models, right? And then they would immediately multiply that by the gradient. That has an effect essentially constructing your very basic first order Taylor approximation of how loss, which is a model output that we care about, would actually be affected by change by a corrupted model in that particular way. What we realize is, well, obviously for quantization, we're concerned about weights, not really necessary activations, because weights are generally just fine gradients we're actually running to obtain a compressed model. So instead of doing this subtraction on the activations, we simply do it on the weights. But the same principle applies, right? Because you can make the gradient to both the weights and the activations. And actually, you get is if you had a clean model that is uncompressed and a corrupt model that is compressed, right? You can take the difference between those two models, and you can predict how quantizing a particular weight will affect the final loss. And we simply estimate what will be the sort of the correct model by quantizing it without extracting any outliers. So you just run a quantization run without our new technique of localizing weights to preserve, and you get the sort of expected difference, expected effect of the quantization on the weight. Apply that by the gradient, you get exactly what is the expected output perturbation quantizing a particular weight. Right, so that's quite good, but unfortunately, it's really unstable because we're essentially making an estimation. Like we're saying, let us quantize the model uniformly, normally, without any tricks, and estimate what the average change of a weight would be. Except obviously that might be slightly inaccurate. So we turn to another idea to basically stabilize it with a slightly more robust trick, and this is what we're calling the magnitude shade gradient, which has a lot of different relatives in different areas. But the one that sort of inspired us to this is the whole line lift, right? And with sort of input gradient kind of attribution right? Layer-wise propagation, relevance propagation type methods, where basically observe that even though a lot of people have invented like fancy ways of basically guiding back propagation to figure out what inputs are really relevant to the model producing output, a lot of them happen to reduce to the gradient multiplied by literally the input itself, the magnitude of the input itself, right? And we realize you can actually look at the model as not as the inputs being the inputs, the inputs being the weights. Right? The way you would look at it when you're training the model. So it's a well-established way of looking at it, right? But there is in fact sort of two ways of looking at the model. Either you change the inputs, you phrase frozen, and you get different outputs given different inputs, or you freeze the inputs and you change the weights, and you get different outputs because you change the weights, right? Quantization is exactly the second sort of thing that we look at. And by treating the weight, therefore, as inputs, you can do the same thing where you have the weights, magnitude, multiplied by the gradient, then you sort of get this sort of generalized idea of how important it is. Right? Basically, what would be the effect if you were to remove a weight entirely from the network? Right? And it happens that this sort of metric does make a lot of sense, and so people do it also in because what we're doing is removing entire weights from the network, and this is to like really stabilize our results. Yeah. So generally, there's a lot of like it's like pretty clear that this kind of method for selecting outliers is significantly more effective than the previous methods for selecting outliers. So squeeze LM basically is the gradient squared, which is sort of like a approximation of the Fisher information, which is, in my opinion, is not a good approximation of Fisher information, but it's sort of like it's similar, it's almost exactly the same as the gradient because it's just the square root of the gradient. And SPQ uses like a localized score based on the quantization algorithm itself, but it's like layer-wise. So it's like looking at if I were to perturb a particular weight, how would that affect the output of a particular layer? And that I want to preserve the output of the layer such that it looks similar to the output of the layer prior to quantization. That doesn't really consider directly the output of the model, which is what in most cases we're concerned with. You can't, people usually do not code from the middle of the model. That's possible. Yeah. So I won't go too hand in on the results because it's like a comparison against like prior methods of quantization. But there's some like interesting like ablation things that we do. So well, it turns out interestingly conditioning matters, and if you were to sort of use data sets in order to find weights are like if you did a intersection between the weights the metric gives says are important on like MMLU versus weight important for K, for example, right? So it's like a more generalized setting. And the intersection is very like 0.3, something like this, right? So 30%. So 70% of the weights are like different. 7% of the weights are like sort of very their importance are different for different tasks. And we see this pretty clearly in the effect as well. So if you were to, so this is, we're evaluating MLU humanities. And then if you were to use wiki text, which is like sort of general pre-training data, in order to which weights are more important. You get like 31%, which is not great because the bottom is 5%. So this is like 6% above random. Right? But if you were to use STEM, a part of MMU, you get better, but it's still not as good. It's like a different subsection of the MMU questions. But then if you use humanities, like you've increased the accuracy by 60% already, just by using a different set to select what neuron is important. Right? And then you think, wow, okay, it's like pretty intuitive insight, but the entire literature has like essentially ignored conditioning. In fact, they implement their calibration data in such that it's possible to use anything other than like the pre-trained data samples because they import like equal length of calibration data samples, and it takes like a non-trivial amount of edits to actually make their algorithm be able to use like examples of lengths, which is kind of funny. But yeah, large impact, and probably also ignored because most people do 4 quantization, and so 3-bit and 2 quantization are like 6x compression, 8x compression, and right now 3-bit is still like iffy. You know, like, people can make it work, right? 2-bit is like it does not work generally. But yeah, for 3-bit we can push like 6x compression and like basically full recovery, like 96, 97% recovery of the original performance on a data set. If we did conditioning and we did our new method for selecting which weights are important. Okay, so also we have analysis on the metrics for finding out what weights are important. So it turns out if you were to just use the weights, so like what weights are best, it like really does not do great at all. If you used a Fisher information, which basically that performs approximately the same as if you were just absolute value gradient, like slightly worse, but basically it's like using noise. And if you were to not take absolute value, you get very, very bad approximation because the gradient cancels out between different training examples. Because sometimes it's one example says update this weight, so it's larger, and then the next example says update this weight, it's smaller. And but what we're really interested in is how much absolute terms it affects the output of the model. Because we want to preserve absolutely the performance of the model, whether or not it's good or it's bad. Then we've got the parts I talked about, so the quantization aware localization, which is using related quantization to figure out the approximate impact of the loss. Right? So if you add that on top of the simple absolute gradient, right, which is part of this metric, then you get a pretty visible boost, 5 points, right? And then if you did the thing where you had like a weight multiplied by the gradients, then you get also similar boosts, right? But then if you combine them together, you also get another boost out of them, like sort of co-stabilizing each other. You get like at least like 5, 6 points above just using gradient. Yeah, there's some other interesting tips here there, but yeah, if anyone has any questions or comments, then maybe this is the time.
Yeah. You chose the ones that had the biggest effect on output for the weights.
Mhm.
What happened when you did the lowest impact weights for output? What happened to the results?
Right, okay. So we didn't test specifically selecting the lowest value weights, but we know from prior papers and also from just like using basically metrics or less correlated with the final output, that effect is like essentially zero. Like the importance of weights is like super like polynomial distribution. So the like in fact the paper that shows essentially there are a few neurons, like actually a countable number of neurons, 5 or 6 neurons, that if you were to accidentally quantize them, destroy the performance of the model. If you were to sort of if you were to preserve them, then it like much increase the model's performance a lot. So those 4 or 5 neurons. But if you were to preserve like even a billion other neurons, like other random neurons, it would not even have like close to the same effect. It would basically have no effect.
Oh.
Yeah. Yeah. So like for example here, this is let's see. You actually see. So this is basically the magnitude of weight, which is still like a okay kind of metric. If you look at the 2-bit,
I feel like using the instead.
It was kind of so interestingly, I thought we were actually using weights when I first read the papers. I mean, maybe I can even find the paper here. There it is. I thought all these papers that are like based on sort of automated were like based on weights, and then when I heard them talk about like connections, I thought they were talking about like actual connections, but it's like a much more abstract form, right? It's like basically a particular head would be one component, and then the connection would be the fact that this component is connected by the residual stream to other components that come after it. And I thought about that for a while, and then because I was thinking they used weights, I tried doing that to the weights, and I discovered we're not talking about weights; they were talking about activation. Then I was like, okay, this is interesting. I wonder why it like worked, and then do some reading and research to figure that out. But yeah, it's because I was reading this literature and I was like, wow. So the first thing was that I read is the ACC paper. I didn't use the gradient at all, and then the next paper I read, a few papers, the edge attribution patching, like outperforms automated discovery, as well as some of the blog posts on edge attribution patching. And they introduced the idea of like efficiently using the gradient to estimate the impact of a particular activation difference. And I was like, wow, that's like very much better than like, because that actually makes it possible to do it on weight level. Otherwise, you have to remove each weight individually, and then there's 80 billion weights, and then like, so you have to run 4 past 8 billion times. It becomes impossible. But they introduced the idea of using the gradient. It's like, okay, this could like actually work, and it did. That's nice. Any other comments or anything that's like unclear or something like that? if not, then there are some kind of other interesting things. Let me see. Okay, so we've got qualitative resistance and stuff. So it turns out the gradient is stable reason in terms of analysis. We use only 188 samples to calibrate the quantization of models. And that translates to like 260 basically multiple choice question prompts, right? But those are just like a sort of like a 5-shot prompt appended to the start of it. And I was like, okay, well, that's a reasonable enough amount to use, so we use that amount. But it turns out if you were to reduce the number of examples you use to 16, so it could be examples as in like because all the quantization does this thing where like fixed length examples. 16 examples means 16 times 2048 sequence length. So 16 times 2048 tokens. Basically, translate that to a token budget, and this is how many multiple choice questions that we enter as input. But even with this tiny amount of data points, it basically sees accuracy. Like the grade does not change at all. I think the effect starts to degrade as you do like 5 data points. Which is, I think that's a kind of interesting thing, like training as well. Because if you were to, I guess, use a lot of training examples that are similar, but at least somewhat different. Like if you're starting from NLP, there's like math questions, right? There's also these questions, there's legal questions, and they're all different. But even though that's the case, our gradient is still stable, which is just that in some sense the sort of training dynamics are also very stable. Like at any given model state, perhaps is a selection of neurons that are the most to update at that moment. And this is regardless of what kind of data that you have. Perhaps directions are being different, but maybe there is some frontier set of neurons that are important at that point, or will to impact the loss more. This has been a pretty consistent finding as well. Interesting to a lot of people. We do scale to larger models. It turns out we can do 8x compression if we used a 32D model, because larger models are generally much easier to quantize. Qualitative, well, there it is. So it turns out if you were to quantize these models, then they basically giving you bad outputs, and it's kind of fun to see like how they fell. So if the value on tap basically translate to SQL queries, and if your contact is in 8x compression, then basically the other standard method give you like just complete failure. And this is like consistently give you empty all the time. For this method, SNOM, we observed a interestingly loose their instruction following ability, but they're still able to give you like somewhat radical sentences. It's just that even though we asked them to answer with a SQL query, it has basically not this, and it's not able to use that. If you have a quantization method that's like slightly less, like slightly more extreme, so this method we actually have to evaluate them at bit quantization, which is like binary quantization. Each bit is represented only as 2 possible values. for each row, for each group of weights. So every 16 weights, there is exactly 2 possible values that these 16 weights could take on for each weight in that 16 weight group. And completely gibberish, which is interesting. Did not know that was a thing that could happen very easily, but it's like go at X path. Sometimes it's not even characters that it could actually put into latex without like trivial amounts of edits. And then sometimes repeats, like this level of compression repeats happen where you get just like complete repeats of like 1.1 and things like this. Yeah, our method is the only one that consistently gives essentially like coherent results. Our accuracy is still not high on this, right? But like, at least they're like basically looking at results that look like SQL. Yeah. Any or something like this? Please feel free. Oh, let me see if there's chat them. Okay. Bye. Yeah. I guess can I ask some questions? Everyone who's in attendance. All right. I guess no objections. What is the general sort of feeling of like applying interpretability to sort of different like applications like compression and things like this? I've heard at least I've heard like one person say that they really don't want to see interpretability being applied to compressing models or making these models better, because it's like then the models get better faster and then you can't interpret them as well, and AI doomsday kind of things. How prevalent is this thought? Maybe you think anyway.
I think I kind of used to think that, but I think that in practice what happens, even if people, like, you're not going to get interpretability that helps with text or whatever without having it be helpful for capabilities in some way. In practice, if people don't find way to improve models with capability, they're going to, the big companies are just going to do some kind of big search to get the same improvement without having to figure anything out anyway. But I have heard like people, like I heard some, I know a list of some case of people tell me they have some way of doing better quantization with Mech Interp, about I don't
Oh, okay, so heard of other people doing like this sort of quantization and interpretability thing? Is that
I don't know what it is. I know of something so vaguely like that, but that person didn't want to publish some thought process sounds like the thing that I did want to improve. I also don't know, how the thing actually because they didn't actually want to code it. So maybe it just didn't actually work and they just, fool themselves or something. Maybe it didn't work. But yeah, I understand why people say that. I personally think it's a good idea to not publish work with, to not do interpretability because of kind of consideration. But yeah, basically that.
Oh, that last part I didn't hear clearly. It's good to not is a good reason not to publish.
I think it's not a good like thing. I think it's also writing something on that. Okay, I'll finish saying it. So I think it's not. I think people should stop doing interpretability because it might capabilities, even though it's probably not. Um, I think it's. Let me try to other methods a bit. Okay, it's true that researching interpretability could be useful to capabilities, and in some sense, capabilities advancing too fast. It might be a bad thing, precisely because I might kill everyone.
That is a
I
concern.
think in practice, it's not a good idea for people. People shouldn't stop doing interpretability because of that. And like, if we want to get good enough interpretability to actually help with identity, we are going to need to actually understand a lot about how models work. That is going to help capabilities like this. Like you completely understood how GPT-3 or something work or GPT-4 work perfectly. You could. There is going to be some ways you can delete some that are not very useful or categorize some of it to be more efficient or make some change in architecture that makes some like maybe there is some part that would work better if you run on some faster serial loop or the model if you actually understand how it works. But
Yeah.
if people don't figure that out, what's going to happen instead is that people are uh, just throw a lot more GPU at it and keep advancing without having any idea what they're doing. That seems like more likely than badly where we actually understand how it works, but it goes a bit faster because of that. The main, I think the main, uh, main thing that makes AI advanced at this point is mostly like how many GPUs the big companies have. Again, the algorithmic advances are they mostly more GPUs to try things. So gradient steps, but more gradient steps to try things out. So I don't think this has any where people, or like even this, for example, your thing is not going to not how like it might improve for some specific class, but it's going I don't know, make the model much efficient at everything or something. Or like it's not, it might be a cool thing, it's not going to be a big deal on the big scheme of things or something. To understand why people might be, some people may be wary of that kind of, like, of user interpretability or something like that. Or like there was some paper talking about where they use the lens to weight many models a bit more efficient, and some people were talking about that. I don't remember the name and what exactly it was. And in the end, it was just not that big a deal.
Yeah,
I don't know.
yeah. I think that's generally my perspective as well. I feel like interpretability is most applicable in a lot of cases. I think probably in compression and efficiency, which is basically saying that unless the improved capabilities can be like threatening just with the ability to essentially run models, hopefully not, probably going to be the case. And but it seems like at least if you were to improve a model's performance by understanding some part of how it behaves, and then use that to improve performance, in that case, then let's use more compute. And now we don't know how it got better, but it did. Yay!
Like that seems less likely to go badly. Yes. Like if we improve if we're improving the models because we know, I don't know, how intelligent we are making it based on that, and we know to like a massive scary wall that the one where we're just, yeah, we throw a bunch of millions GPUs to this, we can do that, we have no idea how it is. So, I mean, I will be worried when he figures out something like, oh, I can train the models 10 faster with this simple trick that we figured out with interpretability or something. And so maybe some quantization trick like this would look like that, and that would maybe say, but yeah, that would, I guess that would look something like during training to find some way of playing with quantization or something. I don't think anyone has figured out something like that. And it seems like you don't much interpretability to do that. They find something like it. They might be just doing the usual thing of just, I don't know, randomly typing randomly deleting parts of models, things like that, and seeing how it improves performance, or taking gradient or something. I guess mostly.
Yeah,
I see on work some. I see some work on it. I'm not sure I understand what you. Maybe because I kept talking at, I don't have the context on when you say it. Context on when you say it.
Hello?
Yeah, I can hear you.
Can you hear me?
Yes. Yeah.
Yeah, I just spent like most of the researchers kind of stop you from like publishing, but they are kind of weird, I guess. That's what I mean. It was the question related to Mech Interp and doing
Oh
this
yeah.
to help.
Mm,
Yeah, I don't think people. Yeah, I think people are mostly okay with this kind of thing, but I think some people are like worried. But for example, recently on his video about I think on his recent video he put on his YouTube channel, what I said, he uh, yeah, he also said he thinks that uh, I mentioned that I think people say that working very helps probably. I think one of his as is on the with his maths and he also said something like that. He thinks that the world where we are, yes, knowing, understanding how this work is going to improve capabilities, probably, but that's any getting much better safety is probably going to improve capabilities. So if you focus too much of let's not improve capabilities, you are probably not going to figure out how to make the model safe. But you're going to have a lot of problems. You might try to, okay, let's try to do this kind of research in secret or something. And I had some thoughts like that a few years ago. I like when this server started, and I had like more. I was thinking, okay, maybe the channel is private by default or something. But I that's in the end that's kind of says that being silly because you can't do useful science, especially get other people to use your thing. You never publish or anything. You're going to have people do things in public. I don't maybe like worried about specific thing. Maybe you want to wait until you make sure that your thing can be dangerous or something in some cases. This you are not. You're probably going to. People are probably going to come up with the same things. So it's not like not publishing is not a good strategy. Like,
yeah, definitely makes sense. I mean, grouping
yeah,
is so
it's true that there is a lot of people who think some bad or like not thinking easily there. I see a lot of people complain about. And to some extent, I had some thoughts like that myself before, but I just thought more about it that kind of realized kind of silly and not. I feel like a lot of these that do not wanted to put things is also down for some Elias post about it, and uh, and I think their call like me should probably publish more things. That's another. Anyway, yeah. Apart from that, don't have much to say about the paper specifically because to be honest, I was distracted by something else. And that's a thing. But for what I did here, it was cool, I guess. I I guess the interesting case where so you are doing like you are using if I understand correctly, you are using the like using the neurons as the basis of which things you are doing, which parts matter. Uh, I think it's interesting related to things like the spatial colors and superposition and things like that. Uh, but I guess this is methods where, like, if I you couldn't really you want to do quantization on the on the weights or the specific weights. So it doesn't make sense to, for example, uses partial encoders activations to do interventions on, you are actually trying to do quantization with a neuron basis. Kind of this is what, like, in other cases of Mech Interp, like, people don't want to use like the neurons as the unit of analysis because it doesn't seem like the models necessarily divide neatly on that tech analysis because neurons can be more than different things. But I just think it's interesting that you have in your use kind of have to you care about which neurons are involved, basically.
Yeah. And it's not even neurons in this case, it's weights, whereas
Yeah.
a neuron is a row, right? Essentially.
Yeah, you will like specific specific connections with neurons.
Yeah, which is, I feel like that's fine. Like, I'm not sure what the calculus is, but I feel like weights are at least somewhat as if you did a autoencoder and you had a bunch of expanded layer, but obviously it's not sparse or like monosyllabic, so it's the unfortunate part.
Yeah.
But there's been some work on, like, I guess, more interpretability focused work where people show like a particular set of weights are more important for a particular like task, and you scale those weights and you get increased performance of the task just by making those weights.
The steering vectors literature, yeah.
Yeah, and the steering vector things as well. It's like, yeah. Oh, I had a thought, then it escaped me.
Yeah. Like, because I feel it doesn't seem like it would have much for this if you had like a better decomposition on the like if you had a better decomposition of modeling in terms of, I don't know, sets of neurons that in something or like some space. Still will care about how that aligns with the weights anyway. So it's not. I guess maybe. Like, I think I wonder if you have some better, like if there was some better way of models where to run ACDC on it, get better, like you can get better lower loss in the data set you're using without less, with less interface things. I wonder if there is you will actually use your method. If you could use something like your method to get better performance, quantization from that.
There's I mean, these methods can give like what modules are more important, and a lot of work on have some modules be in higher bit position and some modules lower position, depending on their relative importance determined by some factor. The factor could be any like stability metric even. But yeah, generally my opinion is those don't work too well because they're not granular enough. Like the particular head is not immensely less important than some other particular head. And also heads are too small. Honestly, that's mainly the problem because a lot of the weights are in the MLP layers, and there are no heads in the MLP layers, so it's not granular enough to do much. But yeah.
Have you tried adjusting the weights for non-NLP neurons? Like, no, just outside NLP. What were the results when you tried doing like attention or maybe the layer ones?
Yeah, so We don't consider layer norms, but we do attention. So we do the K projection, B projection, O projection, and obviously the Q projection as well. So we do all these things because ultimately what happens is that they're all like linear projections. So they're a linear projection layer apply this technique. And interestingly, the importance of these like Curie projections generally is much higher than in the MLP. So maybe I can find a graph, but I don't. But it's generally the case that if we were to take the mean of the importance for neurons in the MLP layer, it's like maybe 2 or 3 times less than the importance of neurons in the Q projection, for example. But it does work. It's the same thing.
Thank you.
But yeah, there's a nice conservation property. Like I'm not sure, particularly if the Q projections are important because so much that there's like a special like architectural reason for it, but more because this like input times gradient thing is iterative. That if you had basically like all of the if you have a module and then you have a certain amount of importance spread up across this module for each weight, then you pass that layer and you get to the next layer, and let's say the next layer is like much bigger, like 10 times bigger than the previous layer. Well, then the amount of importance in that layer also has to be the same as the amount of importance of the previous layer. So that the consequence of which is that it just spreads out, and then you have like less average importance. It's kind of interesting. It is wild that this in fact occurs because the gradient is not really way, and you suddenly you multiply it with the magnitude of the weight, and like, well, now it's conservative. Well, it's a sequence of training dynamic.
There was a similar paper, like there was a paper that I don't remember seeing on the poster session, like clear at some point, where I think they started doing they were reducing the time of some pieces or something, and they found you could do optimization and find some parts of the model that you could delete. They would increase performance in some data set.
Yeah, that is a really incredible. I've seen, I believe, steering literature that has this as well. You do like delete a head. Sometimes there's like bad heads and like good heads for a particular task. If you delete a head, it sometimes increases performance. Yeah.
Yeah. It seems like the models a lot. So maybe that there are more tasks. It seems like it's possible that some parts of the models are just not very useful, or like artifacts of training, and you delete them to get better performance sometimes.
Yeah.
Or maybe they are doing some weird obscure thing that doesn't matter. Some tasks we don't care about, like I don't know, memorizing some weird fact about some obscure thing on the internet, and that kind of thing.
Yeah, it's like in the like there's like addition ahead and stuff like this where like some heads promote a particular token, the other heads like increase the rank of that particular token, and so like, on a rank base, then like you obviously you just want the ones that default the correct token, and there's like I guess more general cases as well where there's just like heads in general that are bad.
I guess in that case, like the innovation case, it made the case that they don't work in that situation, but in some other case you don't get that token and they are working correctly. I guess that they are misfired on that specific situation. But yeah.
And previous to this work, I was doing like calibration of language models and how you make sure you can trust them and stuff like this. And that had a lot of like, so people have like, confidence neurons and whatnot, and they're like, well, some it appears that confidence is calibrated by some groups of neurons, and some neurons would make it more overconfident, some neurons less overconfident. And I think it's too hard to tell like what kind of thing to remove because it's limited by the data set you tested on, which is always very limited.
Yeah, I guess it does the kind of thing where you need to actually understand how the model works. You need something like, I don't know, Anthropic figures out their bars and colors kind of thing, and they make something like the recent paper, but with very have big graph for all of the how all the model works, and then we will know what each part do. But it feels like from that.
I'm not even sure, like, if you were to do that, it would work. Like, imagine how many nodes that would be and how long it would take for you to parse.
I don't know, probably like automate or think, but probably see things on different levels of abstraction with more or less granularity, and say like, okay, so this part is for math or something, or you can also think you can look more into it and say, okay, so this part does addition and this does this other math operation and this does whatever. I think Nora Belrose was talking about on Twitter some weird ideas about how this kind of thing will work because she was saying models have like it makes sense to say models have like mechanisms. I understand her very well anyways, but
It's like I guess it's just way too entangled and it's actually impossible to context. But I guess I do agree with the point that if you have something automated interpretability, then it can be scalable.
What's missing for good automated interpretability? A big part of what's missing is something like a sparse encoders but better, where you take the model, you divide it something that something like sparse encoder the direction. Yeah, some other way of dividing modeling individual parts that makes that have individual meanings in some sense, and then you could do something like ACC and automatically circuits with that. But it's like main problem methods we don't have right now is that we don't have like a good way of dividing models where you take those parts and see how they connect and have like sensical explanations. Or like you can sometimes have this person the I don't know the math feature and if it's connected to the English feature or whatever. You don't. There is no good way of doing that. Maybe there is no way. It's just invisible. But it doesn't use whether it is. I don't know if I'm making a lot of sense right now.
I think it's making some level of sense, but like it is hard. I guess the also angulators have some problems like variability of seeds and like
I think those are not like have not a very good way of untangle things. I think part of it is just assume the underlying representations are like actions in some ways, and seems like there's some linear things going on. That's some of it. There's a bunch of other problems, like sparsity might not be the right thing to look for. There are some then like there are some high frequency features that happen on almost all of the inputs, and those seems to be meaningful. Like there are some things like the position on the positional encoding.
Oh,
Yeah, like me also, I think Jason mentioned on the chat that yeah, the different team in general kind of stop working with person code because they don't think they are very like promising anymore. Because I believe the purpose is that they try person code kind of useful problems, like can they use them to do sting and things like that. And they found that they were worse linear probes most of the time. So that feels like I think they are this thing, like if the person coders were good, could probably find something where they are useful. I'm sure I completely agree with some of these posts, but that's kind of the general thing that people like that the person coders have. They also like have that good reconstruction error and things like that. I think it's interesting working people look at why sparse encoders don't work. I'm trying to come up with better things like transcoder or whatever, materials sparse encoders. The better encoders are about another problem, which is feature absorption. I don't like remember good enough to explain right now what but there are different problems for sparse encoders. There is a bunch of sparse encoders. Maybe someone will come up with something better as person coders that solves the kind of problem. It feels to me like that's one of the main things. Like if we did have something that solves the problems that the sparse encoders are trying to solve, maybe it will be to do better. Better automatic interpretability or something like that.
that is. Oh, can I guess since we're getting on in the time, can I guess if anyone has any more questions, I have sort of two closing remarks, I guess.
Yeah, if we get a bit in case of people have questions, then when you want, I can after the closing remarks, I can close the recording.
All right.
I was mostly talking because I saw other people much. I didn't want this to be just you talking alone 1 hour. So I decided to talk about some things. But yeah,
All right.
anyone else feel free to ask your last questions.
Yeah. So the oh wow, that's sad. Okay. Okay. Two closing things, right? I guess yeah, I think there's a decent amount of things that are just like gradient related. I think the opinion is more from this perspective. I think the interesting part that should focus on is like how do you control these like sort of models? There has to be a good kind of metric to figure out what types of interpretability is better than other types of interpretability. I think a rather good way of understanding that is like how much can you affect the model's performance on things. Like if you find ways of localizing particular behaviors of the model robust, then you can say we have actually found that this part of the model or this intervention can in fact affect them. And then other things is I'm quite curious what is the thought on like using the weight as the unit of analysis interpretability. Like, I think at least so far I'm not seeing much work that uses weights. Like it's either like stop at neurons and say neurons are interpretable enough. Never go to weights. And then usually in neurons, people will say neurons are not interpretable enough, and therefore need to move outside of neurons to some like other kind of encoding or stuff like this. Maybe I just missed a bunch of work that talked about like interpretability with weights. Anyone have any?
So I think specifically about weights is people usually people system coders are like about the activations and not the actual weights, and there is some work on trying to interpret like the weights of the model. With I think the DeepMind thing talks a bit about that, cross coders and everything, but I don't know that much about that. I need to put more of those papers in the reading feed to make myself read them. And I thought people are looking for ways of some sparse data where you have a few activating things that, like, you summarize some activations in some smaller amount of things. Like with the first encoders, you are trying to expand it to have only a few features activation. And yeah. I guess weights in some sense like worse than neurons because you have even more things to
that's
thing. But at the same time, maybe it makes sense to I don't know. I have to think one of that. I have a clear.
I'm biased. I think weights are much better than neurons and a lot of other things. Because that's the thing that you actually train. You know? And I think training determines a lot of how models behave. You have to look at the products of that training.
Yeah, I guess you could train like the neurons instead on the like for a first encoder. You could train a first encoder, for example, on the activation interface instead of on the activation of the neurons.
Yeah, but I mean,
I usually if anyone tries that.
Well, that's probably super really hard.
Yeah, more expensive computation.
Yeah.
But maybe that's just what people are not saying because it's just working with weights. In some sense, exponentially worse than working with neurons.
At least
quadratically worse.
Yeah. Okay. Last question before I drop off, guys. Do you see any work on like interpreting what quantization does? Like I've started to feel that this is like a pretty important area because I have not seen people deploy a unquantized model ever.
Yeah, I don't. I think there is some, but I don't remember. You should probably ask on the chat or something, and maybe someone will have some paper to link. I don't remember that paper I mentioned earlier where there was where they weren't doing quantization, but there was something else they come up with where they were reducing dimensions on the zero on the model and see what happens. There is probably something with quantization. I wouldn't be surprised if, for example, Eleuthera has published something about quantization because that's like a kind of table. But yeah, that I don't remember right now.
Should I use like a questions chat or something?
I think there is a questions. Yeah, there is a questions chat. You can try asking there and someone will answer. I think another thing is you can go to the level AI server with a lot more people there and ask if the people know about that kind of thing.
Yeah. Thanks for joining, everyone. It's straightforward
for doing the presentation.
Yeah. Thanks.
I stopped the recording.